Industry 4.0 was first introduced in 2011 by German Trade and Invest, and they defined it as a paradigm shift made possible by technological advances which constitute a reversal of conventional production process logic. Industry 4.0 is a state in which manufacturing systems and the objects they create are not simply connected, drawing physical information into the digital realm, but also communicate, analyze, and use that information to drive further intelligent action back to the physical world. Let's examine a brief history of the key developments in industrial evolution. The introduction of the power loom in 1784 paved the way for mechanization of production facilities with water and steam power. Electrification made possible the first assembly lines, which were used in slaughterhouses in 1870. This leads to mass production in a variety of industries. The development of the first programmable logic controller, or PLC, came in 1969. The growing application of electronics and IT combined led to automation of production processes, usually common repetitive tasks. Our current revolution is the increasing use of cyber physical systems. This presentation will be focused on smart factories and their role in the changing manufacturing landscape. Cyber physical systems, or CPS, are technologies that marry the digital and physical world, typically via sensors or data within the factory model, to networking technologies that collect the resulting data. It is the leap from connected digital technologies to the creation of a physical object that constitutes the essence of the Industry 4.0 concept. Currently, a host of connected technologies is advancing rapidly, including high-quality sensors, more reliable and powerful networks, high-performance computing robotics, artificial intelligence, and cognitive technologies and augmented reality. Manufacturing leaders have the opportunity to develop improved operations strategies and to realize key business objectives based on the intelligence gained in this new process. The impetus for becoming a digital enterprise is not about who has the coolest technology, but who can best achieve advantage without disruption. Discrete and process industries at all levels of maturity and companies of all sizes are forging a path to digitalization through integrating islands of data to gain systemic visibility and enhanced production control, enhanced engineering and design through software that enables virtual design and rapid prototyping, performing robotic remote diagnostics, and running simulations to predict and plan for maintenance. Many analysts trace the roots of the industrial Internet of Things back to the Lean Six Sigma discipline of DMAIC. As more data is being collected by more devices and methods, analytics can now drive processes and operational decision-making, creating the physical to cyber to physical connection. Virtually all industry analysts have predicted an explosive growth in the coming years. An example of this is how Lufthansa is using an IoT-based strategy to create an entirely new business, mining data from their maintenance, repair, and overhaul operations. The implementation of IIoT will be an iterative process. As more intelligent equipment is utilized, the factory data will be increasing. Eventually, everything in the worldwide enterprise can be connected. Through rapid advances in technology, the ability to work virtually in 3D is now common, and the cornerstone of the smart factory is the 3D model. Only in a 3D model can you have a true view of the operations, equipment in a production environment. Because of the complexity of industrial automation, 3D technology has been utilized for over 15 years. The demands of shorter cycle times required planning, modeling, and simulation for verification before any work was done at the plant. It was imperative to have an accurate as-built model of the plant in order to utilize the new digital technologies. Probably the greatest impact of 3D factory technology has been the reduction in construction times. All design and validation can be done digitally with assurance of accuracy before the plant is scheduled for shutdown maintenance. This also results in reduction or elimination of field change orders, greater project control and collaboration. Going forward, the plant will have a complete asset database of all equipment installed on the shop floor. Everything on the production floor can be identified with associated data. This could include manufacturer specifications, maintenance records, and performance data. This creates not only a visualization and collaboration tool, but a single source of truth. Instead of spending hours manually sketching out factory assets, you can now get them for free from ever-increasing libraries of parametric factory objects. Factory design software now includes a wide range of smart objects, such as conveyors, material handling equipment, robots, electrical equipment, and facilities content. And it makes it easy to resize and edit assets based on your layout requirements. 3D Factory enables you to create compelling 3D visual fly-throughs and walkthroughs of your machine layouts and share it with your clients and non-technical stakeholders. This not only enables you to clearly communicate your layout ideas in 3D, but also helps you differentiate yourself over someone who's communicating layout ideas in 2D. Identify any potential problems before equipment is installed or commissioned on the factory floor, and still create traditional 2D paper deliverables for your installation team, all from the same source data. When done correctly, 3D Factory should streamline the product to tooling to manufacturing process, allowing for faster, lower risk changes. To elaborate, let's say the product designer of a camshaft adjusts the size of the cams for a new engine. In the traditional workflow, this change would slowly propagate through the process. It may take a month or more for that single change to be reflected in the CNC machine that will make the part, and then several more weeks for that new machine to find its way into a plant layout. With an integrated smart factory, once the change is approved, a parametric update will occur, automatically adjusting the CNC and then the plant layout. This can occur in almost real time. Direct nuts and bolts manufacturing capabilities will be improved by the use of autonomous robots and the latest additive manufacturing techniques, also known as 3D printing. Multiple capacity robots bring flexibility and cooperative behavior to manufacturing and have the ability to learn from each other and work safely alongside humans. During the design process, models for true as-built conditions can be created in far less time than designed from manual measurements. To visualize proposed changes, new elements can be added to the model to evaluate multiple scenarios. COBE, or Construction Operations Building Information Exchange, was developed by a number of U.S. public agencies to improve the handover process to the building operator's owners or commissioning. The primary goal is to ensure that owners receive the information about the facility in as complete and as useful a format as possible. COBE is a non-proprietary format based on a multiple-page spreadsheet which can be integrated with the 3D model for visualization and collaboration. All of the building elements can be identified with their associated documentation, such as warranty and maintenance log, in a single source. This will allow for more accuracy in maintenance planning, asset management, and provide the data to generate capital improvement budgets. Using point clouds and fabrication CAD data, we can achieve enough design confidence to enable full off-site fabrication. In 2002, General Motors began using 3D models and laser scanning to quickly update the layouts for the existing general assembly and body shop facilities internationally. Quickly adapting the process as a key use in future program modifications. PMC has converted and completed over 8 million square feet of plant floor to functioning 3D models. Using 3D digital engineering, cycle times can be reduced, field change orders eliminated, with overall cost reductions. The basis for Industry 4.0 is the tight integration among all entities incorporating information technology and operational technology of the enterprise, including the shop floor, supply chain, and back office operations. The interrelated, interconnected, learning-capable manufacturing world of Industry 4.0 has the capability to bring unparalleled levels of efficiency in every sense of the concept to 21st century manufacturing. So why is this important to the leadership of today's manufacturing companies? The bottom line can be summed up in that single word, efficiency. Let's examine some of the possibilities. In a demand sensing environment, downstream data such as customer, supply chain, or channel data is employed to identify demand trends, provide advanced warning of problems, and remove the latency between plan of what is really happening in the supply chain. The quicker deviations can be identified, the quicker and more intelligently a company can respond. The dynamic configurability of supply networks that Industry 4.0 promises requires greater visibility into the entire value chain, including real-time data from the production floor. To respond as quickly as possible to planned and unplanned events, the supply chain needs to be transparent. This in turn increases productivity and reduces risk. Mass customization requires a connection of production capabilities with the supply chain based on a clear understanding and translation of fluctuating demand patterns into targeted production units. To achieve agility and supply resiliency without compromising time to market, supply networks will need realignment. Advanced yet accurate planning and scheduling is possible with the reconciliation of real-time production events and planned data in ERP systems. An automobile OEM used sensors on their fork truck fleet to optimize labor, fuel usage, and damage. Over time, data trends could give a clear vision of the operations and intelligence needed to make cost savings changes. Connectivity to and communication with the larger industrial infrastructure via the IIoT carries advantages also. Notification or sensing of a reduction in electrical power delivery capability could allow the offlining of non-essential devices, reducing electrical power demand and reducing the danger of brownouts or blackouts while minimizing the interruption of vital operations. This capability would extend to other supplied services such as water or natural gas or other fuels. Energy modules within current 3D plant simulation software optimizes manufacturing line energy use. Imagine communication-enabled, interconnected machines that monitor their own condition and operability and can schedule needed maintenance operations. Based on this capability, workload can be automatically shifted away from a machine in downtime to other machines or facilities, eliminating or at least minimizing machine downtime and production. One of the biggest obstacles in implementing Industry 4.0 initiatives is that many legacy factories remain in 2D formats. Factories are generally very dense with equipment, people, and machinery. A traditional 2D layout will only depict a single layer, usually on the shop floor. Cable trays, conveyors, and piping systems will frequently go undetected in these plans, making clash detection difficult to impossible. These interferences will result in field change orders, project delays, and cost overruns. A true 3D as-built condition is required for efficient collaboration and project control. This graphic depicts the transformation of a 3D laser scan point cloud on the left to a 3D model on the right. Manufacturing used to be about making physical products. Today, however, changes in consumer demand, the nature of products, the economics of production, and the economics of the value chain have led to major shifts in the way goods are designed, produced, and sold. To succeed in this new landscape, manufacturers must find new ways to create and capture value. Planning, factories, support, all can use Industry 4.0 technologies to transform operations in various ways. Each of these uses of the connected technologies include its own integrated value loop, or IVL, in which manufacturers may encounter bottlenecks that may impede optimal outcomes. In these cases, it is important to identify technology solutions that can address each bottleneck. Large-scale production will always dominate some segments of the value chain, but three other manufacturing models are arising to take advantage of new opportunities: distributed small-scale local manufacturing, loosely coupled manufacturing ecosystems like that in Shenzhen, China, and an increased focus on agile manufacturing methods at larger operations. While each of these models reduces cost, they also reimagine and restructure how products are made with a deep long-term effect on value creation. Rapid advances and convergences in technology, including additive manufacturing, robotics, and materials science, further expand what can be manufactured and how. Now that there are new sources for manufacturing data and unlimited data capture, how can we translate gigabytes into actionable intelligence? While big data is a phrase most commonly associated with the finance and retail sectors, it is maturing in the manufacturing sector, especially with the large amounts of highly trustworthy information using 3D smart factory technology and related systems. Using big data analytics to drive down the number of mistakes made in the real world, in everything from asset design to operations and maintenance, is key. It's far cheaper to get it wrong virtually than in reality. The phrase "if only" should disappear from the lexicon of operations planning, design, and delivery. One example of analytics use is end-to-end process traceability and genealogy. If a product fails, it can be traced back to the conditions under which the product was built and the components that constitute the product, right down to the vendor. This reduces expensive product recalls. There are present and future challenges that need to be addressed. We're already facing a shortage in skilled labor. This will only increase as the growing complexity of manufacturing environments. As more stakeholders across the value chain become connected, questions will arise within the ecosystem regarding who owns the data and how to ensure proper privacy, control, and security. There must also be a constant vigilance to maintain interoperability within the enterprise standards. PMC has 35 years of experience as a leader and innovator in digital engineering for data-driven productivity solutions. This has been the first in a series of manufacturing excellence in the 21st century. Stay tuned for more.